by Boaz Barak from Microsoft Research, and he will tell us about like nuclear arms and stuff.
Thank you, Evgeny. This is a joint work with Alexander Glaser from the Princeton program on security and policy and electrical and mechanical engineering, and Robert Goldstone from the Princeton Plasma Physics Laboratory. And okay, so usually in crypto what we do is most of the time we kind of find digital analogs of physical things like key locks and boxes and sealed envelopes and seals and signatures. Today we're going to do the opposite. It's not, of course, the only thing, the only work that does it. And we're going to take zero-knowledge proofs. And the idea of zero-knowledge proofs, the digital zero-knowledge proofs, and find physical analogs of zero-knowledge proofs. And in this, we follow the footsteps of the paper by Naor, and Reingold that was published in the prestigious Journal of Cryptology, and which is actually a great. I don't know the other papers in that journal, but this is actually a pretty good paper that I recommend people read. And we're going to do some physical zero-knowledge proofs, but not in the context of where is Waldo, but in the context of nuclear disarmament. So generally speaking, I think it's kind of a consensus that the world has more nuclear weapons than it should have, and it's generally agreed upon that we should strive to dismantle a great many of them. It's actually one of the non-proliferation treaty, one of the, basically what it says is that some countries that didn't have nuclear weapons agree not to develop them further, and countries that do have nuclear weapons agree to work toward disarmament. And indeed, like the Russia and the US that together correspond to 95% of the nuclear weapons in the world, both leaders agree that this is actually, they should try to get rid of most of them. And so far, the treaties between the US and Russia had limits on the number of deployed nuclear warheads or missiles, but it's understood that the next goal will be to start not just limiting the number of deployed, but actually dismantling and reducing also those in the stockpiles. And like this is a quote from US President Obama from about 2 weeks ago, that basically saying this. And one component that will this will require is verified warhead dismantlement. And the idea is you just need to verify that I mean, if someone claims that they have dismantled a warhead, you actually want to verify that they did so. And actually, like nuclear treaties is when the phrase "trust but verify" actually was coined or borrowed from Russian by Ronald Reagan, and it's really important, especially as you reduce to low numbers, because now maybe both countries have 10,000 warheads, so it doesn't really matter a few hundreds here or there. But if they drastically reduce their stockpiles to only a couple of hundreds, then if one country had 100 and the other country had 300, maybe the second country that has 300 will start saying, well, maybe we have like 100 to spare to do like a, to do a first strike, and then another 100 to just finish the job. So it's so you kind of really want to make sure that people are not cheating, or at least not too blatantly. And it turns out that this is not just, I mean, obviously treaties like that have like lots of political challenges to get them agreed and implemented, but there is actually also a technical challenge. And this technical challenge is indeed, how do you actually verify that that this warhead is actually a warhead without revealing the design information of the warhead. And it's probably going to surprise many of you, but it turns out that the design of a nuclear warhead is a classified information. So for example, one thing that maybe wouldn't be surprising to cryptographers, but apparently, I guess, was somewhat surprising to people in this area, is then that at some point the Russians agreed to let the Americans take gamma. I think it was in the 60s or 70s. They agreed to let the Americans take a gamma ray spectrum of the cruise missile. And the idea would be that this spectrum shouldn't, will let you authenticate that it's really a nuclear warhead, but it wouldn't reveal design information. But it turned out that it did. So it turned out that you can actually, you can actually, especially if you have auxiliary information, which is like, you have some ideas of how people design nuclear weapons, then if you see the gamma spectrum of one, you can, that actually helps you, that does yield information. So I think it's agreed that, that probably they're not going to do it again. So how do people, so this is a problem that has been well recognized in the community of nuclear verification, and the approach that people have proposed to do that is this information barrier approach. And there are two versions of this, this verification. One is the attribute-based approach, and one is the template-based approach. I'm going to talk about the template-based approach in this talk. So, but this point of information barrier is similar. So the idea is the following thing. You have like some 300 warheads sitting in some storage facility, and you want to show that they are authentic. And the first observation is that you actually can get your hands on one authentic nuclear warhead. And how do you get your hands on one authentic nuclear warhead? You basically choose at random missile site. You go there, make a surprise visit, and you ask them, please go to the top of this missile, take the warhead out, put it in a box. This is with very good likelihood it's going to be an authentic missile. They're not going to have 90% of the deployed missiles be fakes. So we can get our hands on one actual authentic warhead, and then we have reduced the problem to verifying that these 300 things are identical to the template warhead. So how do you test? How do you test that two warheads are the same? So this is the idea. You have this template warhead that you know is authentic, and the test that you don't know if it's authentic. So you put them inside some black box, and inside that box you have some measurements devices, some various measurements devices that are all connected to some computer. And the computer just have, outside the box you just see a light that it's either, green or red. And if it's green, it tells you, yes, these two things are the same, or sufficiently close to another that we consider them the same. And if it's red, it tells you, no, these things are not the same. And assuming that you don't know how to learn, you can't learn anything out of outside from what's going on inside the black box. You only learn if the two things are equal or they're different. And what?
Who designs the box? You need to trust the
So yes, so the box has to be designed in joint effort between. So they have like a cross lab, like U.S. weapon labs design these kind of things together with Russian labs. But indeed, like the problem, and here is an example of this box, and I don't know if this is close enough that Evgeny can actually read the Russian. There is Russian and English, but I think the resolution is not good enough for this thing. So people have designed it, but the two actual, as cryptographers, I think the obvious thing is that the two things that you have to verify is that first, the box cannot be spoofed. There isn't you know, there isn't some logic in that computer that says, you know, if you see this kind of barcode, then put a green light no matter what. Or, and secondly, that it doesn't leak more information than intended, you know, leakage. Maybe the intensity of the green light actually, you know, transmits to you in Morse code the design information that it views. And it's and of course, because it's like a big complicated machine, this kind of verification is harder. And even if they designed it together, maybe one team, they knew of a trapdoor that they kind of injected during the design process, and they didn't share with the other part. So, and the intuition, why do we need a black box? This is kind of obvious to everyone that works in measurement, like this area. You say, because if you make these kind of measurements inside the box that are useful to verify the warhead, then these measurements must necessarily contain sensitive information. So, so their intuition is the obvious statement that you can't prove that a statement is true without revealing information about why it's true. So, for cryptographers, this is not a valid intuition. So, so for cryptographers, we know this concept of zero-knowledge proofs that exactly challenge this intuition. You can actually sometimes prove that a statement is true without revealing information on why it's true. And this is indeed our starting point for this work. So what is our approach? So basically, we want to remove the black box, and we want to ensure that the measurements allow us to compare that these two things are the same, but doesn't reveal information. And we are motivated by zero-knowledge proofs of Goldwasser, Mikhail, and Markov, but the actual techniques we are going to use are come from information theoretic cryptography, and actually very, very simple techniques. Mathematically, nothing very fancy at all we're going to use in this talk. And I think I might actually also finish before an hour and have time to talk about, I don't know, politics or God. And the idea is we're not going to, we are going to have to assume something about the model of physics, something about the physical world, but we want to minimize the assumptions and not to assume that a big complicated machine behaves in a certain way, but argue about much more simple components that actually don't have any electronics or logic in them at all, and so make it so basically minimize the physical requirements. And currently we don't have a system. We have an empty room, some computer simulations, and some bunch of equipment that is arrived or being ordered, but hopefully in several months there will actually be some physical experiments.
Seriously?
Yeah, I mean, my collaborators are serious people. They're not like me, they're actually people that build stuff.
Where did you order the warhead?
What?
Where did you order the warhead?
The warhead. So we actually, my collaborators have already ordered the bowling ball that will serve as they will fill it up with, I think initially nothing radioactive, maybe later some uranium, not weapon grade, to act as a dummy warhead. The idea is if you can show that two objects, if it works for coffee makers, it will probably work for warheads. Is there another question? So, okay. So, what's the rest of the talk? So I'm trying to more formally define the authentication problem, then give some kind of a cartoon of our protocol, and then talk about the implication, and prove it, and I'll hide a few kind of annoying details under the carpet, and maybe I'll mention them later. So we have two parties. So usually they're called Alice and Bob, but for this application I just call them Anastasia and Bob. So And one of them is the party that's being inspected, that claims the words are the same, and one of them is the party that inspects. And they engage in a protocol to verify that two objects are close to each other. And completeness is that if they are close, the objects are close to each other, and both sides follow the protocol, they actually Bob will accept the proof with high probability. Soundness, which is in that literature is called sometimes authentication, is that if X is far from X prime, then regardless what Anastasia tries to cheat, Bob will actually find out and reject the proof. And the zero knowledge property, which is called certification in that literature, is that if they are similar and Anastasia does what she's supposed to do, then we are talking about information statistical zero knowledge, or then let's say that what Bob learns is statistically independent. The distribution is independent of what was the actual input, or generally the notion we'll get is some kind of like epsilon zero knowledge. So say you have small mutual information that has small statistical distance from some a priori distribution. Okay, so here is a cartoon of our protocol. So suppose that the two objects are basically Anastasia has two cups. It's like this one, and she has inside each cup like a bunch of marbles, and she wants to show to prove that the two cups have the same amount of same number of marbles inside them. So that's what it means that they are similar. They have the same number of marbles. So here is a protocol to do that. So she wants to reveal this to prove this to Bob without revealing the actual number. And here is a protocol to do that. So she prepares 10 pairs of big buckets. I guess like this trash can over there, or maybe I should have brought some props with me. And in each bucket, she pulls like a large number, like capital N is much larger than small n number of buckets, but number of marbles. But it has each pair of buckets has the same number. So in each pair, there is the same number of marbles, but between different pairs, it's just different independently random numbers. Now, Bob chooses one of the pairs of buckets at random. And he doesn't look at how many marbles are inside this pair, but the others he takes and he counts and he counts and sees that they do indeed contain an identical number of marbles. So now we are left with this pair, and Anastasia. So both buckets contain some Ri. We took the ith pair, so both marbles contain the Ri marbles. And Anastasia pulls down the marbles to the buckets. Now both of them contain X plus Ri marbles. And Bob, they should contain the same number. And Bob accepts the proof if indeed then Bob counts the actual number of marbles inside the buckets. And he accepts the proof if they both contain the same number. So soundness is kind of obvious. Like you'd say, if the cups contain a different number of marbles, then Bob will reject it with probability at least 0.9, because if the probability, if you had the only way that they will accept the only way that Bob will accept the proof is if the pair of buckets didn't contain an identical number of marbles to begin with, but that's only. Then it will be caught with 0.9 probability. And the zero knowledge property is that the number that Bob sees is X plus Ri. So it's basically, it's not the uniform distribution between 0 and capital N, but it's shifted by small x, which is at most small n. So the statistical distance between the uniform distribution between 0 and capital N and this distribution shifted by small n is at most small n over capital N. So if we make that small enough, we get kind of epsilon zero knowledge. So Bob didn't learn much about the original number x. So So basically, this is the principle behind our protocol, and this is the math that we use. And so now, what do we do? How do we go from cartoon to implementation? Then
Like the protocols.
version of Schnorr, right?
No, Schnorr, for proving something is a square or not. Exactly the challenge response, right?
I mean, I guess
Just your notion of the distribution is different.
yeah, I mean, it's clearly very, very.
No,
you know,
I'm not saying.
Yes.
I'm just saying it's really one-to-one in some sense, right?
Perhaps, I
It's
mean.
a kind of, you're opening up all the envelopes except for one.
Yes.
And then you're counting, right?
Yeah, I mean, in some sense, I guess yeah, I mean, we kind of make some physical assumptions that like are not exactly. Yeah, I mean, there's obviously cut and choose here, which is exactly the same, and then we kind of use some physical assumptions about, say, buckets and that don't exactly. I don't know if they have like exact. I'm not sure if like we would think of it as some homomorphic commitment that you can add two things together and then get like pooling the marbles might be. You would think that you could homomorphically add two encryptions to each other, but
Earlier encryption.
maybe yes. You can. So how do we actually? Yes, unfortunately, like there is not much application for the. I mean, I think that maybe both countries should also work on reducing their stockpile of marbles, but right now they're more interested in warheads. So what do we do? So we start by thinking what would be like a non-zero knowledge protocol for this task. How did you actually measure the two things are the same, regardless of if you thought about secrecy? And there are various approaches to do that. We take one particular approach, which is that you subject each, you have these two words in containers, and you subject each container to a source of neutrons. So you fire at it some neutrons, sufficiently, not too many, so you're not going to start too big of a nuclear reaction. Although you do actually create a little bit of fission, that's because you actually want to measure that there exists something in there that creates. So you fire one neutron and not just one comes out, more than one. And the idea you kind of put like a circle around the object with an array of detectors. And you're going to, it's like taking a picture. You're going to measure how many neutrons arrive at each detector. So basically, it's some kind of taking a picture of this, or an X-ray, if you think about it, with neutrons of this object. And it turns out that this picture is, presumably, this is actually part that we don't have an analytic proof of that. And in some sense, you really can't, but this is the part that's really most supported by computer simulations, that it seems that you could, that if the two objects are actually have very similar pictures, then they are similar for our purposes. And so this is just some simulation. So the picture will look something like this, say. And which is actually if you look at the picture, you actually learn about the design of the thing. So it's not a good, it's not zero knowledge by any means. And if you compare the two pictures of, you take two pictures of two similar things, they will look kind of similar. And if you compare two pictures of two, you took one warhead where you took a little bit maybe of the nuclear material out of it, then you'll actually see a difference. So our notion of being similar will be that this picture is similar. And here is you might actually have to, if you actually do the protocol, you might actually have to be a little bit more delicate about this. Select the energies of the neutrons, right, and focus on some particular areas, but let's not go into these kind of details. So another way to just phrase the same thing, that the two pictures are similar, is that if you were to pick a random position of a detector, I'm thinking of it a random position theta of where exactly you're going to place a detector, then if they were similar, then you would probably see the same count. And if they are far apart, then you would likely see something different. Of course, you're going to amplify this by repetition, but let's just say that you're going to get some noticeable difference. If they're different, you're going to see some noticeable difference.
So you're counting, a count vector looks like the picture on the left?
Yes.
You're counting...
So this looks like a picture on the left, and this is a case where I subtracted two pictures taking from like two different, like two very similar objects.
Right.
And this is a case where I subtracted two pictures from one object was, say, an authentic word, and the other one was one where I took out some of the nuclear material. And so you see that there are much more differences here.
So you're saying now that if you put only one detector in a random theta, in a random
Yes.
place, then
The probability that the count is the same will differ significantly between the two cases. So by repetition, you can kind of, you'll need to pick some threshold and do some repetition, but generally there will be a big difference between the probability that the two things agree if the objects are the same, and the two things agree if the objects are not the same. And let's say for simplicity that they will perfectly agree if the object is the same, and they will be very different if the object is not the same. But in the actual thing, you'll actually need to pick more than one position if you wanted to get to that point.
so you know they know this is can be shown formally,
No.
or is it by experiment?
This part is like by simulation, because in some sense you could have objects that are different and have the same detector count. Like in particular, maybe you would have like maybe this object is actually some shield that blocks all neutrons, and then it has its own source that projects the picture of the other thing.
Visibility cloak.
Yes. So
What about completeness? So if things are the same, they will.
if things are the same, yes. If it's the same object, you're going to get the same count. You know, up to some statistical noise that you always. But if they are different, you have to say that the different in the case that we kind of care about, and is that in the differences in the case that we care about, these kind of measurements will tell us. It's not perfect identity of these objects for all. I mean, it's a little bit like having like you take an X-ray. So two things. Generally, we say two things have the same, but you could have like things that don't show up in an X-ray. Or
An X-ray also is important. Who reads it?
what? Who reads it? Yeah, I mean, yeah, but generally, if you just want to say if two things are the same, if two people are the same, the X-ray will tell you some properties of them, but might not tell you all the properties of them. So, okay, so this is would be one way to do it if we didn't care about zero knowledge. We'd say just publish this picture, or maybe even just publish one point out of this picture, and that will be enough to distinguish them. So how do we actually implement? And again, we kind of cheat because we're going to repeat several times. We're going to maybe use some different energies. So basically, Anastasia is going to prepare 10 pairs of detectors. This is our corresponding thing to the original buckets. And she initializes the two detectors in each pair to an identical random initial value. So the detectors don't start. Usually detector is kind of a counter. It starts with 0 and you fire neutrons at it, and it then tells you how many neutrons it saw. This one is not going to start with 0. She's going to initialize it to some random number Ri. The detectors we are currently planning on using are these bubble detectors. There is nothing electronic about them. They're just this material that if it hits the neutron, a bubble is formed. So she's going to, you can think of it a little bit like film in a camera. So she's going to pre-expose that those bubble detectors to some neutrons before we even start. Shafi, you had a question? So, so this is, so she prepares these pairs of detectors, and basically this Ri, you can think of it as the number of marbles in the bucket. Then again, Bob will select 9 out of the 10 pairs to examine. He wants to see that they have the same number, and he actually wants to see maybe that they actually also work as a detector and if you fire more neutrons at them, this number increases. They're made from this white material. And then Bob selects a random position theta, and they place a detector from the remaining pair in the theta positions of the template and the void. So we have two remaining detectors that Bob hadn't looked at, and we place them at the theta position in the test and the theta position in the template, and we run the neutron source for t seconds, and we measure the counts. So Bob now gets the detectors and he measures the counts, and he learns basically x plus Ri. If the two things are the same, then it's the same number x, the number of neutrons that we'll, the new neutrons that we'll see, and he learns this number x plus Ri, which is exactly the number that he learned before in the marble experiment. So the protocol will be epsilon zero knowledge, where epsilon is like n over capital N, where small n is some upper bound that we have on the number of on the number of neutrons that we're going to see in t seconds. So this is basically it. The actual thing, there are like more complications because you have to kind of work with the dynamic range of these bubble detectors versus the amount of noise you want to add, and you kind of might want to separate energies and do these kind of things. But basically, this is the idea. Yes.
Wouldn't just having a thick wall
What?
on the outside of the warhead, like a thick wall on the outside of the warhead, wouldn't that also cause problems for you? Like if the warhead just had a nice thick.
So if the detector count in some sense was zero, zero always, yes. So in some sense, this is kind of the so these could be like two objects that, but notice that one of these objects is the template that you took from an actual. That you took from an actual warhead. So maybe if today they designed new warheads and they thought of this test in mind, they would say, okay, we don't mind, we're going to lose, we're going to make our missiles a little bit less efficient, but we're going to cover them with this neutron blocking material so that we could pass the test. But since But the idea or the hope is, which I'm not qualified to to evaluate, is that that actually if you look at current warheads, because remember the thing is one of them is a template. So in this sense we kind of
so you can at least detect if something funny is going on.
Yeah, in some sense you can't. Like it's zero knowledge. So if you will not detect if that the two.
Oh right, that's right.
So in some sense you're not going to detect. I mean, one way that the two warheads could have like an identical neutron signatures is if they were both covered in completely blocking material. I'm not sure which material it is. I think it's cadmium or something. There is some material that blocks neutrons completely.
But you haven't actually verified this, so it could be the fact that the way nuclear missiles are generated creates what we would call a puff. Yeah, that it might be that it actually generates, when you do this test, you actually get random stuff back.
Random is good because it will probably be unique random for different.
But then you couldn't compare two to each other. If the actual signal came back that actually due to the manufacturing process, the signals coming back were always different between two different warheads, your test wouldn't work.
That's actually if it was different between different words. I mean, different words of the same type.
Yes.
Yes. I mean, this is part where like this computer simulations come into play, and part where if this work were to proceed forward, at some point probably the people that will have to continue this kind of process will have to be people that have the necessary clearances to actually know if this thing works or not. I mean, all I can say is that my co-authors are not completely, they are in this area. I mean, they're not, government agents.
As far as you know.
As far as I know. Well, I mean, actually, the Princeton Physics Plasma Laboratory is owned by the federal government, but yes, this is based on unclassified information, and in some sense, this is as much as we can do.
But on the other hand, if your test fails for this reason, you've actually created a cryptographic object in the sense that each warhead can act as a physically unclonable function. So you then may be able to use it in some other program.
Maybe you can pay with words. I mean, it's more useful than it's more useful than money. I mean. So this is actually the last technical slide. I only have conclusion after it, so more questions are very welcome.
So epsilon is non-negligible, right?
Epsilon is non-negligible, and
What do you think? Is it necessary? I mean,
okay.
So can you imagine a model where you can prove?
So yes, I can imagine a model where we'll have epsilon equals to 0, which is another kind of variant, but then you have to make more physical assumptions. If by some magical way you had a detector that that managed to give you not a count. I mean, it's not magical. You can do it with electronics. It's just we're trying to avoid electronics. But with electronics, you can have a detector that doesn't give you the number of neutrons you saw, but maybe gives you just the 10th digit of that number. And then you could do, your noise will be like a one-time pad. So you will have epsilon equals to 0. You'll have perfect noise. But there is another way that you could still learn something, which is that probably the two warheads are not completely identical. And you will learn that. I mean, even if they are not completely identical, then this is something that you learn actually in your protocol. This is one fact that you actually learn, and in fact you also learn at which position, because the position is in the clear. There are some other variants where you select several positions and you
position
and there's some other variants which might be useful for this, where you select several positions and then you shuffle them before you measure the actual number, so you to hide the actual position that you saw. But
maybe you'll learn the relative ages of the warhead or something like this.
yes, I think this is actually the neutrons are not accurate enough, which is actually something you want to learn. You want to see, are they trying to get rid of the old useless thing? But in some sense, that's one thing that this measurement is apparently not sensitive enough to detect the age of the warheads. Yes?
You started off showing the spectrum, which I understood was some sort of semi-unique signature. Why don't you take another spectrum, have each party throw in a bunch of random radioactive debris to offset it?
So, in some sense, we are using a different signature, which is also, it's a different signature, which is also, and in some sense, in some sense you can say, instead of adding the noise to the detector, you could add the noise to the object. There is something maybe a little bit cleaner about the noise to the detector. Also, maybe you don't want to let the other party fiddle with the object too much because of things like what Amit said. But this is like some alternative. You could say allow them to, you have this container, allow them to drop one more object of their choosing inside the container to mask the original thing, but which is will have very similar effect to adding this thing to the detectors. But in some sense, the detectors are taking a different spectrum. It's just somehow very, very simple, and they have these bubbles, and it's very concrete. So you kind of hope that. First of all, it actually could be the inspector party that prepares these bubbles, and second, you hope that maybe the bubbles don't contain a transmitter that. Or it's hard to, you can't really observe from the outside as neutrons. They don't click, unlike maybe electronic detectors. They don't kind of click when they see a neutron. They just form a bubble, and you might not hear it So this is kind of like you're worried about these kind of side channel attacks. But you might, I mean, there are very different, this general thing could be instantiated in different ways, and I don't know if we hit on the right thing, and it might well be that as we explore it further, we see that different versions should be used. Yes?
Is like rational crypto useful in this context?
What?
Is rational crypto useful in this context? I mean,
Rational?
yeah, if you can't cheat, but you might get caught, and you're not going to do that because you know that they will stop being tracked. So.
Do you see Sylvia's talk?
No, I missed Sylvia's talk, but I think that in some, I mean, there is some sense that zero knowledge always has some kind of rational element in the sense that, for example, the protocol is only zero knowledge if the statement is actually true and you actually follow the protocol. So we don't guarantee cheaters any secrecy property. Like usually in zero knowledge, you only guarantee zero knowledge for the honest prover. If the prover is dishonest, they don't get zero knowledge. And so one thing, I mean, obviously, so you assume that also that, like, say, Anastasia wants to pass the protocol, and some things like select a random offset. She can select a non-random offset. It's just it just hurts her zero knowledge, so it's kind of in her interest. And there are like some other, but there are maybe more, I don't know if it's more relevant to you. I mean, like nuclear disarmament is a complicated process, and there are other safeguards in place. So in some sense, I think that after like maybe 10 years after you dismantle these warheads, they are all, somebody is going to check that from the end of that pipeline comes out the remaining nuclear material that you would have expected if it was warheads and not coffee makers. So there are, it's not the only, yeah, in some sense, yeah, so in some sense, very blatant cheating would be, if it detected, might have like serious consequences. But
It's clear that your map is collision resistant because the signatures that you constructed, because you kind of assume for soundness that something which is not a nuclear warhead will have a different signature or whatever.
no, it's
Is
not.
it clear that it's not collision resistant?
No, it's not. Like I say, it's not collision resistant.
Well, that it is collision resistant because otherwise it's like I'll just observe the real the spectrum on the warhead, then I'll just construct a coffee maker which has the same spectrum and.
Yes.
then
So
it's
so the question is how could you construct something that's completely. And I think in principle you could,
But the point is you're sending neutrons, which is a test for fissile material, right? You're testing.
yeah, some of it, but you could maybe. I mean, you might be able to construct a completely different object that has a similar signature, and there is a question.
Part of the problem, right? I mean, the way I see it, because if you're saying the stakes are high. And people really don't want to disarm.
No, I don't know if they don't want to disarm. So you might have like this is also why I said like in some sense you might you might be able to construct a completely different object, like in particular a shield. Like you construct an object that containing two things, like a shield and a projector itself. That maybe when you press a button, you tell it how.
Right.
So you could think of an active, like an active object inside, and probably, like I said, it will have to be combined with different things. Like you might compare weights, or you might, like say, in 10 years actually check that some actual things came out. So some of the people in this area, they want the verification. They're maybe not that worried about completely. Kind of things that as cryptographers we think of, and they might have their reasons.
Oh, but to be honest, I mean, if people really, I mean, it costs some money, but in principle, if Russia wants to kind of cheat, I mean, they can just produce more nuclear weapons without anybody noticing. And I mean, it's expensive, but this way they will have more than they claim. But
yes, I'm not completely sure how does it work. I mean, I think they also like. There is also some kind of safeguards in place. Every country knows where the other countries' facilities are, and probably takes satellite photos of them all the time. And so there are. This is just one component of a very complicated process, which at the end is kind of in the interest of both nations. They really are, you could argue if they want to get to zero nuclear weapons, but clearly, like, destroying the world once is good enough. They don't need to destroy it 100 times over.
So what venue are you considering? Is it similar venue as Moni for publication of this?
I don't know if we can get accepted. It's actually, wow, I forgot the name. We are going to present this in the conference for, I think, international measurements and nuclear measurements or something like that in June in Florida, or August in Florida. I remember, I forgot when exactly. It's in the summer in Florida, if anyone wants to come. It's, I think it's the conference on so I think conference on nuclear measurements or something of that form.
As I mentioned to Boaz earlier, actually the use of cryptography in nuclear treaty verification is quite old. There's work of Gus Simmons going back to the 80s, where he looks at monitoring stations for missile silos.
Yes, I think they use a lot of crypto, actually digital crypto, inside these things. Like basically, this whole thing is very complicated, and at some points you need to basically go to the other guy's plant and maybe put in a box something, and then you put something that basically some camera of yours that sends you a digitally signed picture every second to see that nothing fishy is going on.
The signature has to be deterministic.
Yeah, that's the thing that to avoid side channel attacks, and you need deterministic signatures. It's very complicated, and probably like other areas of work. The crypto is already helping, and maybe more crypto could help more. And I guess this is basically it. We don't completely get rid of this information barrier approach, but we kind of minimize the use of it, and we so far have only computer simulations, but we hope to have at some point actual experiments, not with nuclear warheads. Although I live in Boston, so if they want to experiment in Princeton, then it's fine.
Plasma department also in.
What?
There's plasma physics also in MIT.
In MIT, no, but if they want to experiment with actual warheads, I prefer that they do it over there. But we're not going to actually do experiments with words, but with other like objects that the principle should be similar. Yes.
So for getting hold of the template, in the current kind of disarmament protocols that they have, do they actually allow somebody to pick a random warhead and go and get a hold? Because presumably, let's say Russia wouldn't allow, U.S. inspectors to just pick a random warhead anywhere in Russia and go and.
Well, it will have to be, I guess, part of the treaty that you do allow it. The locations are not secret. The locations of where each country has their missiles is not secret.
You think so?
No, I think they actually tell one another exactly the locations of where they have. They count on quantity and not secrecy to avoid and quantity in submarines, I guess. So I think so. In principle, like the U.S. could knows the list of places where Russia has missiles, and they could select a random one and say, okay, please, take us there, and it has to be part of the treaty, of course, that this is allowed. And
previous treaties have done verification of actual missiles. So this is about the warheads.
Yes.
If you've got procedures in place to count missiles, you know where a missile is.
Yes.
So you know where that, or in some sense.
Yes, you know the numbers,
Yeah.
and I think you actually know where they are. Like, so far they have a lot of restrictions on. So they didn't restrict how many words you have in your stockpile, but they have a lot of restrictions and a lot of declarations and verifications about the actual the missiles.
Do your colleagues have any policy influence? I mean, are they consultants for anybody who might actually make a decision with respect?
So I think they are involved in this kind of this whole this whole research area of policy and security. And these are things that I don't think they themselves have any influence, but they would know who the people that they could propose this thing to. And this is, I guess, one. I mean, the salt treaties are very complicated, but it's one kind of thing that to say that these people, I guess, people have in their community been uncomfortable with the idea of this information barrier approach because it's really big, complicated machines that you don't really understand, and people have kind of distrust of complicated machines. So if you just present a more simple, it's good to know that something like that is possible. Yes.
What is meant as the warhead?
What?
What is meant as the warhead?
So my understanding is, again, it's pretty limited, but my understanding is that the idea is that so the Russians dismantled their own warhead. The idea is that they have like a building which has only one entrance and one exit, both monitored by Americans. Americans don't know what goes on inside the building, and in some sense they verify the word when it comes into the building, and at some point there will come some junk out of the building that they will also verify, and it could take years. But the only dismantling is going on inside this sealed building, and I don't know. Presumably, if there is a war between the US and Russia, the first thing that they will bomb is that building. So you wouldn't be able to use it even if you haven't dismantled.
So this firing business is happening, because I forget already. So they dismantle it. Where is this firing neutron thing happening? In the building?
So I guess in the entrance to the building, something like that, you would want to verify, or maybe even before that, like at some point, maybe you would want to verify it, and then they'll put it in some queue, some things that are supposed to enter into the building, or something like that. It might be in several places actually along the chain that you would want to verify these things. Yes.
If you have a trusted third party, maybe it could help with the reprocessing, like
What?
Canada.
Yes, I mean, if you trust anyone, yes, it would be.
Well, it depends if there are grants involved.
Did your co-authors come to you or to propose this, or did you?
So they actually my co-authors so they started with like my co-author Alexander Glaser. He had like a lunch with the dean of the faculty in Princeton, David Dobkin, who's a computer scientist, and he said I guess David asked him what he's doing, and he said, this is a problem working. He said, well, this sounds like zero knowledge, and then he started searching online about zero knowledge, and he came to me, and then we started.
This was a black box paper, okay?
What?
Because of your black box paper,
No, not because of the black box. It's actually because of Nature survey by Bernard Chazelle that mentioned the work of me and Amit about concurrent.
No, but that would be really funny if it was because of your non-black box simulation.
Non-black box. Yes, because it is indeed like it's a non-black box. It's another non-black box zero knowledge.
It's the most practical application of your paper.
Yeah, maybe we should call it non-black box zero knowledge.
Non-black box.
Yes.
All right, so I guess you should have lunch and time go out.